Break. Yes. Put back a slide. That one? Another one? That one. Yes, cool. Right, let's have a break. I shall start again at 3 o'clock. Right then, let's carry on. So, we've talked about what happens when we've got a sine tone carrier and a sine tone modulating signal. So as in this case, we've got our carrier at 1 kilohertz, and we've got a sine tone modulating signal at, in this case, nearly 200 hertz. When we modulate that, we get this carrier in the middle, unchanged carrier signal, and then we get integer multiples of pairs of sidebands spaced by integer multiples of. If our modulation index is modulate that, we get this carrier in the middle, which is unchanged carrier signal, and then we get integer multiples of pairs of sidebands spaced by integer multiples of our carrier frequency, so of our modulating frequency. What happens if we put into this a more complex modulating signal? It sounds weird. Apart from it sounds weird. You get many frequencies. I'll do that. We'll be a bit more specific. So using that depiction that we used before, where we can draw the sidebands as either the right way up, the correct side, or the inverted, the wrong way up side, compared to how the modulating signal was to start with, we can do a similar thing here, where we've got our carrier component, we've got our first set of sidebands, so this is our audio signal, and that's 20 hertz to 20 kilohertz, 40 hertz up to for an infinite frequency range. And so, okay, I'm not quite going to demonstrate that, but if we turn it to an audio signal, turn that on. So you can see, based on the spectrum of that signal we're listening to, those bands are moving, or those sidebands are moving in and out, depending on what the primary spectral components are of that signal. But again, it's symmetrical around that centre frequency. Or if we were to put some noise in there, again, we see that spreading out on each side, and it's multiple components. And as we increase the modulating signal level, we get crazier and crazier. Or if we do our audio signal again and we turn it up, what's that going to do? Etc. That's enough of that. Cool. One more thing, something that somebody asked me during the break was just to explain a bit more about what this modulation index is. Pop back a slide. That one? Another one? And we've got sine tone modulating signal at, in this case, nearly 200 hertz. When we modulate that, we get this carrier in the middle, which is unchanged carrier signal, and then we get integer multiples of pairs of sidebands spaced by integer multiples of our carrier frequency, so of our modulating frequency. What happens if we put into this a more complex modulating signal? It sounds weird. Apart from it sounds weird.
You get many frequencies. You do it. Like what component?
And then we have changes, modulate that, and the lower sideband will go down plus that value will be something. For a given modulator, but that would take a set even left of the fourth set. We can see divided by our modulation frequency plus our modulating frequency. What's the next one? I'll go through it. So let's look at what we have here. What?
How do you get? I want to know, like, what technique can you use to derive that? Like theoretically.
What can you use?
Yeah, what's useful to do that?
Why is it useful? Is that the question? Or how do we do it?
What mathematical techniques?
No idea. I found it in a book. You need to talk to a mathematician. See, the other reason why we're doing lots of jiggery pokery and avoiding it is because I'm a bit crap at maths, especially doing it live. Found it in a book. I'm sure if you go and look in a good maths book about, in fact, if you look in the modulation book, which is in the further reading bit at the end, but it'll tell you it there. But the important thing is, what we're doing here is trying to see what the components are that result from FM. What's this first component that we've got out? What's the frequency of that? Yeah, that's our carrier. Now we've got this J component, which is determining its level. We'll talk about the J components in a minute. What's this component that's come out?
That is something that looks like a sideband.
It is a sideband, exactly that. It's a carrier frequency minus the modulating frequency. So that's a sideband just as we had for AM. What's this part? Exactly, the other sideband, that's a carrier plus our modulation, plus or minus twice the modulation frequency, minus the modulation frequency. Another pair of sidebands, plus or minus, getting another pair of sidebands at the carrier minus, plus or minus twice the modulation frequency, carrier plus or minus 3 times the modulation frequency, carrier plus or minus 4 times the modulation frequency, and all the way on, as I say, to infinity or beyond. So, if I go into this here demo, stick that on the screen. Turn it up so you can hear the fun. There you go. So as before, we have a sine tone carrier at 1 kilohertz. We have a modulating signal, which at the moment is 221 hertz. And when we use FM to do the modulation, we're getting the carrier still at 1 kilohertz, a pair of sidebands at plus or minus the modulation frequency, another pair of sidebands at plus or minus twice the modulation frequency. And if I turn this up, oops, there's the next set of sidebands appear, and the next set of sidebands appear, and so on. And we've gone off the end. Yeah. We haven't got on to J yet. That's determining the level. So that gets a little bit more complex. We'll come to that in a second. Hold on, let me just turn this off. Shut up a minute. Yes, question?
Are the other sidebands always there? They're just very low level?
Yes. So the level depends on this J thing that we're going to look at the moment.
Why did the carrier?
The important things to note are we've got lots of sidebands, and all of these are integer multiples of our modulating signal. And so if we reduce our modulation frequency, they all move closer together because the spacing is based on that frequency. And as we move that, increase the frequency of our modulating signal, they all move apart. Similarly, it's all based around our carrier frequency. So as we reduce the level of our carrier frequency, the whole lot moves down or moves up. And basically, FM is brilliant for making lots of cool noises. Right, I'll stop making cool noises and get back to the lecture. Hence why frequency modulation is something that's widely used, or has been widely used for quite a while, in synthesis. Right then, so we know what the spectral